Right, today, so we're going to just do a bit of a review with graphing and stuff, a little sort of math refresher that I'd like to start the year off with, just to make sure that everyone's kind of up to speed. So, for the most part, you should know most of this. This should just sort of be reminders, review that. Now, unfortunately, that smartboard is quite low, isn't it? So if you can't see something, let me know, and I'll try to remember to scroll it up. Okay. Bear with me. I like to use the Symposium. I don't use the smartboard a whole lot. So, okay. So displaying data with graphs. A well-designed graph is more than a picture with 1,000 words. It can give you more information than either words, columns of numbers, or equations. To be useful, however, a graph must be drawn properly. In this section, we will develop the use of graphs to display data. So, graphing data. And that's not what I wanted to happen. Why did it do that? I think I have to actually, maybe I should do this. No? That's okay. Well, that was page, right?
Underneath your recording,
Yeah?
you can hit your scroll bar.
I know, but
Or if you flip it over.
can I move the scroll bar to the left-hand side?
Yeah.
How do I do that? Oh. I'll just sit over there.
Okay. I think it's. I can't see. Move that recording.
Oh, hang on. Sorry. Yeah, I'm just going to... I wish I had a prize to give you. That was awesome. Yeah, we should have kept it on recording, eh? Oh yeah. Thanks, Gil. Okay. So, one of the most important skills to learn driving a car is how to stop it safely. Anybody in driver's ed right now? Nobody. Anybody have done their driver's ed already? Excellent. So you'll all remember this. Perfect. The faster the car is going, the farther it travels before it stops. Well, of course. If you study for a driver's license, you probably found a table in the manual showing how far a car moves beyond the point at which the driver makes a decision to stop. Is that taught in driver's ed? Little manual about braking distance? No one listens. Oh, okay, well. Yeah, okay. So one manual shows that a car travels a certain distance between the time the driver decides to stop the car and the time the brakes are applied. This is called the reaction distance. Highlight that. Or if you're just a pencil underliner, do that. But make sure that gets noticed. Where's the highlighter? No, that's not what I want. Reaction distance is the distance it travels in what time? Between the time the driver decides to stop the car and the time that the brakes are applied. So we're talking about the time you're driving down the car or driving down the road, you see a little kid, oh, better hit the brake. Right? So that time between your brain going, oh, gotta hit the brakes, and your foot actually getting to the brake. How long would that generally be? Hopefully less than a second, right? Your reaction time is hopefully less than a second. So when the brakes are applied, the car slows down and travels the braking distance. I'll do it this way. Braking distance. That's the distance that it actually takes for you to actually brake. Table 1 in the bar graph, figure 1, show these distances together with the total stopping distance for various speeds. Okay, so I'm going to scroll. There we go. Okay. So, original speed. Now, physicists and physics students tend to deal with speeds that are in meters per second, which is obviously how many seconds it takes you to travel 1 meter. I guess that'd be the time, right? So 10 meters per second would, of course, mean you go 10 meters in a second. How fast is 10 meters per second? Is it fast or is it kind of slow? How far is 10 meters? What's the difference between a yard and a meter there, George? I know you like to golf. Well, a yard is how far? Okay, and if I'm pacing it off, it's like, a yard is kind of like a big pace, right? Okay, so that'd be about a yard? About a meter? Meter's a little more, right? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I have to stop it. Basically the width of this room. In a second. That's fast. It's not that fast. Okay? Does anyone know the magic number? How do you know that, Keelan? Oh, good for you. And it's also right here. It's right there. The magic number is 3.6, and 3.6 is the magic number that converts from meters per second to kilometers an hour. And what you do is you multiply. So I'm hoping you all got the memo about the need for a calculator. And if you didn't get the memo, you probably should have figured it out. It's physics. There's going to be calculations. So what I want you to do is I want you to take every one of those meters per second, and I want you to multiply by 3.6 and fill in that column. Okay, so obviously the first one is 36. 15 is 54. Next one, Ryan?
72.
72. You might as well give me the next ones too.
90.
90. I think it's like 102, isn't it?
108.
108? Okay. Okay, so physics aside, let's just talk about this for a brief second. 10 meters per second, the width of this room in a second, we thought was kind of fast, but it turns out it's only about 36 kilometers an hour. Now, if you were riding in a car and Dad was driving 36 kilometers an hour, you'd get frustrated in about 2 seconds, right? Like, pick up the pace, Dad, right? However, that's probably about the speed you should be driving down a narrow residential street, right? I understand. 50 is actually, 50 is 15 meters, that's like from there to there and back in a second. If someone runs out, you've got a second and you've covered that distance. That's pretty quick on a residential street, right? Your road's like 54, that's like, no one's going to complain too much if you're driving 54 down the mountain, right? Or Whitmore or Main Street, right? But if you're driving down a narrow back lane or a residential street, better knock it down to about 10 meters per second. 72, maybe just leaving town, right? You're traveling 20 meters per second. 90, maybe going through the park. If you're a little bit of a speed demon, because it's supposed to be 80, right? That's 25 meters per second. 108, my speedometer doesn't even go that high in my car. I've never even been past 100. Okay, but that would be, I don't even know, 30 meters per second, that's just crazy talk. But that'd be like the length of the whole hallway here. In a second. That's a long ways. You know the lines on the road that tell you when you can pass or not? You know these old lines that are dotted? The dash lines? How long are they, do you know?
They're actually really long.
If you get out of your car and stop, and I recommend you look for traffic both ways before you do so, but they are longer than 10 feet. If you lie down, they are longer than anybody in school, even Mr. Walker. Okay, they are long. When you're traveling at 108, they just look like this, right? They're not lying. They're 10 feet long. Okay, so please slow down a little bit. How long does it take to maybe change the? Because no one wants to listen to 7:30 TKDM. How long does it take to change the radio on your stereo on your car as you're driving down the highway? Fiddle with the stereo a little bit. Well, yeah, I know, yeah. The new cars, right? I've got one like that too. I suppose, okay. 10 seconds? Wow, I better not be riding with you, Ryan. 10 seconds? You be traveling. If Ryan takes his eye off the road for 10 seconds traveling down the highway, he's going to be going 300 meters. Almost like 3/4 the distance around the track. Yeah, you take your eyes off the road for a second and a half, and you're traveling probably 45 meters down the road without looking. Oh yes, and not looking where you're going. Keep that in mind when you're driving. It's kind of freaky. Okay, back to the physics. Okay, so the first step in analyzing the data is to look at them carefully. Which variable did the experimenter or the driver change? In our example, it was the speed of the car. Speed is the independent variable. Have you heard that before, Joey? Independent variable. You have. In math class, I'm guessing. Oh, okay. Sounds good. Or manipulated variable. It's the one that we had some control over, right? The other two variables, reaction distance and braking distance, change as a result of the change in the speed. These quantities are called dependent variables or responding variables. They're the ones that you tend to measure. Right? The independent is the one that you control. I'm going to drive 25 meters per second. And then the dependent is the one that you measure with a ruler or timer or whatever you have. How do the distances change for a given change in speed? Notice the reaction distance increases by about the same amount for each increase in speed. The reaction distance. If you look at these, somebody with a calculator quickly tell me what's the difference between 7.4 and 11.1? Subtract. 3.7? What's the next one? 3.7. They're all about the same, which makes sense because the reaction distance is how far you go in the time it takes you to actually, get your foot to the brake, and you're traveling faster and faster and faster, right? You're traveling at a constant speed, remember. So it would make sense that these should go up by the same amount. Okay? So how do the distances change for a given change in speed? The reaction distance increases by about the same amount. The braking distance, however, increases much more as the speed increases. And if I've got to go back to here, you don't even need to do the math. You can tell here that the braking distance is going up. Like that's 9 to 20, that's about 11. 20 to 36, that's like 16. 36 to 57, that's like 21. They're getting bigger and bigger and bigger. What's that going to look like on a graph? Now, you could do the math here, but if you were to actually see the graph, it wouldn't take you long to realize that here we've got the graph. The reaction distance is this bottom one. Notice that it's a straight line. It's pretty flat, actually. This next one, the middle one here, is the braking distance. What shape is it? It's curved, right? You might guess it's a parabola from math class. What's this top graph here? What do I mean by that? Yeah, the two added together, and it should be no surprise that it's curved. All I've done is just taken this curve and just gone up by this amount of time, so it's going to be exactly the same shape. Okay. So from a graph, a relatively educated person could tell whether it's a linear relationship. Which one of those is linear? The reaction distance or the braking distance? Yeah. Reaction distance. It's kind of a line. And a relatively educated person could tell that the braking distance is not linear, it's curved. And of course, there's many kinds of equations that would give you a curve, and you'd have to investigate a little bit further to see just sort of which one it was. Good so far? Have I bored anybody entirely? Still with me, more or less? Okay. Don't worry, you'll have a chance to do some stuff in a bit. Okay, so just a quick refresher how to plot graphs. I'm not guessing that anyone here has never plotted a graph. I'm sure you all have. So just a quick refresher. Identify the independent and dependent variables. Okay, try to do that without asking me, and try to do it without saying which one goes in the bottom. Right? Think about which one you're controlling and which one you're measuring. The independent variables plot on the horizontal or x-axis, the one down below, right? The dependent variables plot on the vertical or the y-axis. In our example, speed is plotted on the x because I had control over my speed, and distance is plotted on the y-axis. Okay, and that was what we had for our graph here, right? I got speed down here, I got distance there. Determine the range of the independent variable to be plotted. What do I mean by the range? Tell me what do I mean by the range, do you think? Not the place where the buffalo roam at, by the way. No? Range, anyone? I said the range of data. What would you guess? Lowest to highest, exactly. The lowest to the highest. So determine the range of the independent variable to be plotted. In this example, data are given for speeds between 10 and 30. So the range is between 10 and 30. Now, if you could include 0, should you? Like if you can include 0 easily in your graph, should you do so? And the answer is yes, always. 0 is an important sort of benchmark kind of thing. It's an important visual thing. If you can include 0, you should. I didn't. That was bad. Probably Excel did it for me. Okay. So I'm going from 0 to 30. 0 to 40 is perfectly acceptable as well. Decide if the origin is a valid data point. What do I mean by valid data point? If I was, in this case, if I was traveling 0 meters per second, what would be my braking distance? 0. I'm not moving. Is 0, 0 a valid data point? Yes. Yes. Should we include it? Yes, absolutely. Because it's an important visual thing. It's a cue. So when the speed is 0, reaction and stopping distances are obviously both 0. In this case, your graph should include the origin. The origin is 0, 0, right? Spread out the data as much as possible. If you've got a nice big full sheet of graph paper, don't stretch it down into the bottom left-hand corner. Okay, it doesn't make it very easy to see. Let each space on the graph paper stand for a convenient unit. Choose 2 to 5 or 10 spaces to represent 10 meters per second. Number and label a horizontal axis and repeat steps 2 to 4 for the dependent variable. Plot your data points on the graph, and then here's an important one. Draw the best straight line or smooth curve that passes through as many data points as possible. Notice the italics. Do not use a series of straight line segments that connect the dots. Do not connect the dots. Don't do that. Do not do that. Okay? We want what's called a line of best fit or a curve of best fit. Have you ever heard that before? In math class, maybe. Science? Awesome. Line of best fit, curve of best fit. Our most scientific measurements, is it going to be a perfect straight line? Not even close. Is it going to be a perfect curved line? It's your best interpretation of what you think the data is doing. Okay? Computers will help you with that kind of stuff nowadays too. All right, so that's graphing. Let's look at different kinds of relationships here. I'm going to yak for about another 5 or 10 minutes, and you're going to have a chance to do so. Linear, quadratic, and inverse relationships. 3 kinds. Linear. The graph figure 2 of reaction distance versus speed is a straight line. That is, the dependent variable varies linearly with the independent variable. There is a linear relationship between the two variables. The relationship of the two variables shown in this graph can be written as an equation, which I'm hoping you're familiar with. Y equals mx plus b. Give me a nod. Yeah, I've seen y equals mx plus b. M stands for the slope. B is the... What does y-intercept mean? Where it crosses the y-axis, where x equals 0. Right? If I were to draw it right here, I'll start over here. If I were to draw it on this graph here, where would I draw it? Where's the y-intercept? Right there. Right? Where it crosses the y-axis.
Yeah, but the x-axis is
You're right. In this case, it is. My bad again. Not very good. Each constant can be found from the graph. The slope m is the ratio of the vertical change and the horizontal change. You guys probably heard rise over run, that kind of stuff, right? To find the slope, select 2 points A and B as far apart as possible on the line. The vertical change or rise, delta y, is the difference in the vertical values of A and B. The horizontal change, delta x, or the red, is the difference in the horizontal values of A and B. The slope of the graph can then be calculated as. So I picked 2 points. I got 18.5, which looks to be like above, looks like this point here, right? So I picked the y value here, 18.5, and I subtracted 7.4. That looks like it's going to be this one here, right? So the rise, how much it goes up and down, is 11.1. The run is from 10 to 25, which is 15, and we get a slope of what? 0.74. Anybody here has never calculated slope before in their life? Don't know what I'm talking about. Good. Okay. Notice 0.74 what? Seconds. S. What does that mean then? The slope is a? It's a time. Slope is a time. Keep that in the back of your mind for a second, I think. No, I went the wrong way. What's going on? Next page. There we go. Notice that the units have been kept with the variables. That's seconds. The y-intercept B is at the point where the line crosses the y-axis, and the y value when the value of x is 0. In this case, when x is 0, the value of y is 0 meters. For special cases like this, the y-intercept equals 0. The equation is simply y equals mx, and the quantity y varies directly with x. After drawing the graph and obtaining the equation, check to see if the results make sense. You're going to be coming up with equations today. The slope indicates the increased reaction distance for an increase in speed. It has units of meters per second. Let me go back one page, if I can do it properly. What's my unit on top of the equation here? Meters. What's my unit on the bottom? Meters per second. The meters and meters per second, what cancels?
meters.
The meters, and I've got a per seconds. right? The divide is still there, and that divide is still there, so I've got to divide by seconds, and when you kind of flip it upside down, I'll show you how that works in right away, you end up with seconds. Okay? Thus, it is a time. And what time is it? Important here. Not lunchtime, reaction time. How long did it take for this person to get their foot on the brake? 0.74 seconds. Is it going to be the same every time? No, probably not. Not if you were actually doing an experiment, right? However, if the person was concentrating and paying attention, would their reaction time be generally pretty much the same all the time? Like somewhere between 0.7 and 0.8, would you say? Sure. If it's perfectly 0.74, what kind of line am I going to go? What kind of line am I going to get right here? If it's always 0.74, perfectly straight. If it's not always 0.74, then this line's going to be? Is it going to be curved, or is it just going to be kind of like, the dots are going to be kind of like, you know, one there, one there, one there, like kind of straight. Kind of straight. And the more concentrated the person is, likely the straighter it's going to be. Right? Okay. I can see that I'm boring you here. We'll get there quick. All right. So the slope is a property of the system the graph describes. That's important. Slopes always have a meaning. In math class, slopes are just crazy little numbers and go on to the next one. In science, they mean something. I'm going to be asking you, what does the slope mean in this particular case? I'll show you ways that you can come up with that. Okay? Now, the value of y does not always increase with increasing x. If y gets smaller as x gets larger, then the slope is negative, like this, right? Negative slope. Okay. Quadratic relationship. What does the word quadratic mean? I got two more relationships to go. These ones are a little quicker. Parabola. That's the shape of it, right? This is, in fact, you're probably used to parabolas actually being both sides of the u, right? That's when you got negative x's. In science class, they tend to only be that part. How come? Because generally time is not negative. We usually go forward in time. There's only one person I know that goes backwards in time, and he retired last year. Oh, you are awake. Excellent. All right, so parabolas. This indicates that the braking distance varies as the square of the original speed. In other words, if you double your speed, the braking distance increases 4 times. Do you remember that from driver's ed? That's important. Twice as fast, not twice as far to brake, but 4 times as far. 3 times faster, 9 times farther. I'll give you one more chance to get it right. 4 times faster, 16. Excellent. Squared. Squared. So, the graph slope changes, so it cannot be calculated. Can you find the slope of a curve? You cannot. You can, however, calculate the slope of the curve at an instant by drawing a tangent line. Who knows what a tangent line is? Anybody? Occasionally, Mr. Bennett goes off on a tangent. What does that mean? It means, like I said, talking about what I did this summer. You know, I went down to South Dakota and I saw this crazy horse memorial. Have you heard of that before? It's this giant statue that they're blasting out of a mountain. They started carving it in 1948, and all they've got is the guy's face so far. That's how big it is. That's going off on a tangent. What do I mean by a tangent line? It's a line that looks like this. You may not have ever seen this actually, right? It's kind of hard for me to draw because there's not much slope there. But it's a line that, whoops. It's only supposed to touch the curve at one spot. That's a tangent. Okay, and I'm going to show you how to do that in a bit as well. Okay, so based on this graph, if it takes a person 40 meters to stop after driving at 50 kilometers an hour, how far will it take to stop if the driving is 100 kilometers an hour? How much faster are we going? I was starting at 50, now I'm going 100. I'm going twice as fast. So if it took me 40 before, now it's going to take me twice as fast, 4 times farther.
120.
160. Yeah, close enough, eh? It's early. It's September, Ryan. Okay, an inverse relationship. Inverse has that shape. Some relationships are such that as one quantity increases, the other one decreases. For example, the more time you spend talking in class, the lower your mark. Inverse relationship. Its graph would look like figure 5, look like that one there. Again, you may want to determine the instantaneous slope by applying the tangent line method. I'm going to show you more about that in a bit. But if you had to find the slope right there, you would draw a straight line at that point. Pick 2 points on that line and then find the slope. And you're going to be doing that curve. Okay, so I've done enough yakking here. Now these 4 questions, is there 4? Yes, there's 4. These 4 questions are designed to make you think. I've more or less given you the information you need to figure them out. It's not a regurgitation thing. It's like, okay, I got to think here. So take like 10 minutes or so. Work with someone if you need to. See if you can come up with an answer. And we're going to check before the Valentine's bell goes. 2:23. So I'm going to give you to like 2:05, and then we'll reconvene and see where we are at that point. Okay? As a rule, let's do some help. This usually happens, so don't freak out. Don't think, oh, I'm going to fail. We can't do the first 4 questions. It's okay. Suppose a student doing the lab determines that the y-intercept for a graph of reaction distance versus speed was 3.4. What would this mean in real life? We're talking reaction distance versus speed. Now, I have barely taken you to the point where you're going to understand this question, so it's not totally surprising that you're having trouble with this. It's reaction distance versus speed. I drew a little graph down here. If you have something versus something, the first something, in this case the reaction distance, the first something goes where? The y or the x?
Y.
The y. So this is, has anyone ever used the abbreviation for reaction RXN? No? Okay, RXN reaction. Reaction distance versus speed. And I apologize for those of you that may not be able to see that way down low. Reaction distance versus speed. What is reaction distance measured in? Likely meters. It could be kilometers, but likely meters. What is speed likely measured in?
Meters per second.
Meters per second. And when I find the slope is 3.4, I'm talking about reaction distance, meters, over the x, right? Rise over run, the y over the x, meters over meters per second. And we've already seen that meters over meters per second becomes seconds. So what is this 3.4? Before it was 0.74, I think. 0.74? What is the 3.4 in this case? 3.4 seconds, the person's reaction time. They are really slow. The kid is running the street and they're going, oh, wow. 3.4, oh, that's fast! That's a lot of time. That kid is in trouble. Both of them, I guess, right? So yeah, what would it mean in real life? The person is not paying attention. The reaction time is extremely slow. Draw a sketch of what it would look like. Would...
We have to draw.
No, don't draw. That's not what I want. I want a sketch of the graph. Sorry, I should have clarified. If this one is 0.74, what would the graph of slope 3.4 look like?
Where are you getting 0.74?
That was the one we did before, right? Remember the graph we had before? I just want a comparison. What would it look like? Would it be steeper, flatter, or the same?
Steeper and go up more.
Be steeper? Bigger number slope means steeper. Ryan's exactly right. In fact, it'd be like 3 times steeper, wouldn't it? You know what I mean? Okay, it'd be much, much steeper. Exactly. Okay? Much, much steeper, much slower reaction time. Much slower. Okay, now what about number 2? Number 2 you can do, can't you? In the earlier braking example, at what speed is the reaction distance 10 meters? The reaction distance. I got to go to reaction distance. At which speed is the reaction distance 10 meters? Right about there, right? 10 meters is here on the Y, right? At what speed? About a little less than 15, maybe 14 meters per second. At 14 meters per second, your reaction distance is 10. So that's just a can you read a graph question. You got to be able to read a graph in physics. There's no doubt about that. Okay. A graph of reaction distance versus speed is made and the slope is found to be 0.74, like our original. Suppose another experiment is made and the slope is found to be steeper. I think we've already answered this question. What does it mean? Yeah, the reaction time is much slower, a bigger number. Reaction time is much bigger. Now the last one is the hard one. Have you even read the last one yet?
No.
I'm going to give you a minute to read the last one. All right. So here we have the relationship between the circumference and the diameter of a circle. Would a different circle circumference create a different graph? Now, be brave. Hands up if you think different circle would give you a different graph. Hands up. Hannah's so sure she put both hands up. Okay, how many people say no? Different circle, same graph. Oh, half and half. Let's go back and ask again, because now you're feeling a little bit of pressure. Oh, geez. So, yeah. All right, one more try. How many people think different circle, different graph? I was not so sure this time. Only one hand goes up. Okay, now. Okay. New circle, same graph. Oh, we're leaning towards that right now. Well, those of you that switched, good for you, because the answer is. Well, let me just first of all say, how many circles are shown in this graph?
I'm not sure.
More than one. Every circle between 1 and 5. In fact, one could argue there's an infinite number of circles here because there's 1, 2, 3, 4, 5 circles with diameter of 1, 2, 3, 4, 5. There's also circles of 1.5, 2.5, 3.5, 4.5, and 1.2, and 1.3, and 1.4. There's like a bazillion circles shown there already. It's a little bit bigger than a trillion, a bazillion. Okay? This already shows a lot more than one circle. So, of course, you're going to get, there is no such thing as a different circle, circumference, different graph, because it's the same thing. We're already showing tons and tons of different circles here. Now, what is the meaning of the slope in this case? This is a hard question. How do we find the meaning? Well, there's two ways. The first way is to look at the quantities. What's my y quantity? Right here. What am I measuring on the y? Circumference. This is number 4. I'm measuring circumference. Slope is rise over run, so it's circumference over diameter. Now, does anybody happen to know what circumference over diameter is? You're on the right track. Does anyone know the formula for circumference of a circle? Circumference is pi r squared is the area. Anderson, you're real close. Pi times d. Excellent, Jay. Pi times d. Follow up pi, right? Now, if I were to rearrange that so it says c over d, what would I have to do over here? And what would I be left with? C over D equals one way to do it. Oh, Joey's head just exploded. Clean up on aisle 3. That's one way to do it. The other way would be to look at the units. What's the units for the y? Centimeters. What's the units for the x? Uh-oh. If it was meters per second, meters over second, well, that would be clearly a speed. If it was meters over meters per second, it'd be S would be a time, but centimeters over centimeters gives me a... No, centimeters over centimeters cancel and give me a big fat nothing. But what's the units for pi? No units. Pi doesn't have units. Pi is just a plain old number. Okay? So sometimes the quantities will help you, like if you've got meters per second. Sometimes you have to go, the units will help you, centimeters over centimeters. Sometimes you have to go to the quantities to get a good idea what the meaning is. Challenging stuff, there's no doubt about that. Okay? I do not expect everyone, oh yeah, I get that, no problem. Give me the test tomorrow. Okay? We're going to have to practice it. What are the units of the slope?
There's
No units. Big fat nothing. No units. Is there always going to be no units on the slope? No, only when it's a constant. What does the word constant mean? Always the same. 3.14 what? Very good. 3.14 newtons, right? There is no unit. It's not seconds or anything like that. Okay, that is by far enough talking on my part. There's no doubt about that. There are 3 sets of exercises there. You have 223. You have 11 minutes. I will correct the first one tomorrow, Hannah, because I'm not that mean. You only got to do one for tomorrow, but we will do the next 2. If you're not here tomorrow, you should do all 3. You got to have at least the first one done tomorrow. I think it involves some graphics. Am I right?
Yeah.
Is there graph paper there?
Yeah. Where? Well, there's like a picture.
Well, there's a picture. All right, you know what? The first one of this is super easy. Let's do the first 2.
No, let's stick with one.
All right. First one.